Welcome to the evaluation part of soil dynamics course. Today we will start with quiz for this soil dynamics course. This quiz can be taken or you can appear for this quiz or this test after completion of the module which describes about the machine foundations. So, let us see at the questions which are asked in this evaluation or test or quiz. Let us look at the slide here. So, soil dynamics quiz, full marks can be assigned about 100 and duration is 1 hour to solve the number of questions which has been set for this quiz. It is also mentioned answer all questions and assume reasonable data if necessary. If it is not required, of course, all the data have been provided in this question paper set. So, let us look at the question paper set first. This is the first question which says using standard notations for design of machine foundation under vertical mode of vibration by elastic half space model, prove that B times A naught n square is equals to 6, numerical value of 6 for a soil which is having Poisson's ratio of 0.333. So, the marks assigned for this first question, if we look at the slide again, is 20 marks. Let us move to the second question which says prove analytically by using elastic half space model that the exact relationship between coefficient of elastic uniform compression, which generally we express by using the symbol C suffix u, and coefficient of elastic uniform shear, which we generally express using the symbol C suffix tau, is given by Cu equals to 1.4 times C tau for a soil which is having Poisson's ratio of 0.45. So, for this question also about 20 marks can be given. Let us look at the next question. The question number 3 is prove that the slope, that is the tan theta of the Chebotarev's reduced natural frequency line in the linear scale, the graph which we have described in the theory part of this course. So, the same Chebotarev's design chart, we want to find out what is the slope inclination analytically. So, that is what we are asking here, that prove that the slope of that line when we are using the Chebotarev's design chart in linear scale, not the log one, it is in the linear scale, is proportional to this term where this capital G is nothing but the shear modulus of the soil, small g is acceleration due to gravity, and this mu is Poisson's ratio of the soil. Pi is of course pi parameter 22/7. So, marks for this question also can be set as 20 marks. Let us see the last question which can be set for this quiz or for this test. Question number 4, it is asking that compute the factor of safety against liquefaction using the approach proposed by or given by Wood et al. 2001, the paper which we have described or which we have discussed thoroughly in our course curriculum of this soil dynamics course. At a depth of 10 meter below the ground surface for earthquake movement below the ground surface for earthquake moment magnitude MW equals to 6.5 at a site with following available field data. What are those data? Like depth of water table below the ground surface, which is 5 meter. Soil type is loose silty sand with percentage fine is 6%. Saturated unit weight of the soil is 17 kilonewton per meter cube. Friction angle of the soil phi is 31 degree. Relative density of the soil dr is 60%. Corresponding to that, we know the factor f, which needs to be used for a correction factor later on for solving this problem, that f is 0.7. SPT value N60 at 10 meter below the ground level is given as 14. Let us note here that the value of SPT N value given here is corrected using the energy correction. So, that is why the symbol used here is N suffix 60, that is related to 60% of energy input. So, we need not to carry out any energy correction for this value of N60, which is supplied to us or given to us in this question paper. So, N60 at 10 meter depth below the ground level is set as 14. Earthquake zone is given as zone 4 as per our Indian earthquake code IS 1893 with the value of A max, which can be considered as 0.24 times G. The marks for this question can be kept as 40 marks. So, total of 100 marks for this test with these 4 questions. Now, let us see how the solution of these 4 questions can be done with steps and details. What is the possible set of solution we can have for this quiz. For the first question, let us write down the answer. So, let me keep in this slide here the question number 1, so that we can easily write down the solution. It says standard notations of B and A naught n needs to be used. So, using elastic half space model, as we know, as per elastic half space theory or elastic half space model as given by Reasoner in 1936, the expression for the non-dimensional parameter mass ratio is given by B, small b, which is equals to m by rho r naught cube, that we know already, and the non-dimensional frequency parameter A naught n is given as omega n r naught times root over rho by g. Now, in this we know for this parameter B, m is the mass, rho is density, not the unit weight, it is density, r naught is the equivalent radius of the rigid circular footing or machine foundation which is designed, and this A naught n expression omega n is natural frequency of the system, R naught already I have defined, rho I have already defined, and G is shear modulus of the soil. So, now we need to prove in the next step. Let us put it here. The parameter B A naught n square. So, we need to compute this term. Let us see on simplification what we get from this term. So, this will be the expression of B times A naught n square. Now, in this case, this gets cancelled. I have only one R naught, rho gets cancelled. So, what we can write further? It is equals to m omega n square by G times R naught. Now, let us see if we know any other expressions to simplify it further. So, according to Timoshenko and Goodyear 1951, the expression for the stiffness of the system for vertical mode of vibration K can be expressed as 4 G R naught by 1 minus mu. We already know this when we have discussed the theory of machine foundation. Here all the parameters are known. G is shear modulus of soil, R naught is equivalent radius of the circular rigid foundation subjected to vertical mode of vibration, mu is Poisson's ratio of the soil. And we know omega n, that is natural frequency, is expressed as root over k by m. So, using this known expressions, let us see what further simplification of this parameter B A naught n square we can bring. Therefore, B A naught n square, on further simplification, it becomes m times k by m, because it was omega n square, which we can write as k by m, divided by G R naught. Now, this m gets cancelled. So, what I can write? This becomes k by G R naught. Now, what is the expression of k? Just now we have seen for vertical mode of vibration is 4 G R naught by 1 minus mu. So, this gets cancelled. So, 4 by 1 minus mu. So, B times A naught n square can be expressed by this expression, that is 4 by 1 minus mu. This is a very good expression which shows that the product of this non-dimensional mass ratio and the square of the non-dimensional frequency parameter is dependent on the soil property only, and that too on the Poisson's ratio of the soil, which is simplified by this expression. So, now in our question it was asked that if the Poisson's ratio of the soil is given as mu as 0.333, then what should be the value of this term B A naught n square? then let us put in the expression the value of mu. This will give us the solution, B A naught n square equals to 6. So, proved. That was the question which was asked in our first question. If we look at the slide here, it says prove that B times A naught n square is equals to 6 for a soil with Poisson's ratio of 0.333. So, that is what we have established here. This is equals to 6. That completes the problem number 1. Next, let us move to problem number 2. Let us see what was problem number 2 in the slide. Let us skip it here. We need to prove analytically that using elastic half space model, the relationship between C u and C tau, the exact relationship is given by this if the Poisson's ratio of the soil is 0.45. Let us see what we can find out or how we can prove this expression. So, answer of question number 2 now we are writing. What we already know from the theory which has been covered for this course soil dynamics, that K z is given by C u times A. What is K z? K z is nothing but the spring constant for vertical mode of vibrations of a machine foundation system, and C u is already defined as coefficient of elastic uniform compression, and A is the cross sectional area on which the vibration is subjected to for the mode of vertical vibration. And for horizontal mode of vibration, this K x is given as C tau times A. So, K x is the spring constant in the case of horizontal mode of vibrations for a rigid machine foundation, block type machine foundation, which is expressed as C tau. C tau is nothing but coefficient of elastic uniform shear, and A is the cross sectional area of the foundation which participate in this shearing process. So, if we know these two expressions, what we can write? Their ratio, that is K z by K x, that is vertical mode of vibration to horizontal mode of vibration, can be simply written as C u by C tau, because the cross sectional area involved in both the cases are same. Now, just now we have discussed, we have known expression of K z, which is 4 g r naught by 1 minus mu as per Timoshenko and Goodyear 1951. For vertical mode of vibration, G is shear modulus of the soil, R naught is effective radius of the equivalent circular foundation, mu is Poisson's ratio. Similarly, let us see what is the expression for the parameter K x. Now, K x can be written as 32 times 1 minus mu g r naught by 7 minus 8 times mu. This is according to Bycroft as proposed in 1956. We have discussed this also in our theory course. See, if we know the expression of these two terms K z and K x, then automatically in the expression of C u by C tau, we can put them and simplify it further. Let us see how it can be. So, 4 g r naught by 1 minus mu times 7 minus 8 mu by 32 times 1 minus mu into G r naught. So, G r naught gets cancelled 4, 8. Therefore, this C u by C tau becomes 7 minus 8 mu by 8 times 1 minus mu whole square. That is the expression. So, in this expression, now it is given in the question for mu equals to 0.45, we need to find out the exact relationship. So, let us put the value of mu equals to 0.45. So, mu Poisson's ratio is given as 0.45. Therefore, this C u by C tau becomes 7 minus 8 mu by 8 times 1 minus mu whole square. Therefore, C u equals to 1.4 C tau. Hence, proved. So, this shows that for a particular value of Poisson's ratio, there is an exact solution or exact expression or relationship exists between these two parameters C u and C tau, which is established here or proved here. So, this is proved already, that is the solution of question number 2. Let us see what is there in question 3. Question 3 said, prove that the slope of Chebotarev's design chart in linear scale, the reduced natural frequency slope is proportional to this parameter. Now, let us see how we can establish this solution or how we can prove it. So, answer of the third questions we are now trying to find out. As we have already discussed in the theory class for this soil dynamics course, this is a typical chart in linear scale as proposed by Chebotarev for FNR in the x axis and in the y axis we have 1 by 4th root of area A. So, that is the linear scale as proposed by Chebotarev. This is reduced natural frequency in x axis, which is nothing but the natural frequency times root over q naught. Q naught is uniform pressure below the machine foundation, and A is the cross sectional area of the machine foundation. 1 by 4th root of that A in linear scale is in the y axis. Now, for different types of soil, as we have seen earlier, there are different lines given by or proposed by Chebotarev for the design chart. So, this angle, if it is theta, it is asked in this question that prove this tan theta for any particular type of soil. If we look at the slide here again, it says this tan theta, the slope of that line will be proportional to this parameter. So, let us see how we can prove that. So, we need to prove that tan theta is proportional to the parameter which is given is pi to the power 2.5 times 1 minus mu, mu is Poisson's ratio of the soil, by G G. G, capital G is shear modulus of the soil, small g is acceleration due to gravity. So, we need to prove this. Let us see how we can proceed further. If we see the expression of non-dimensional mass ratio B, which we have also discussed in our previous problem number 1 just now, B equals to m by rho r naught cube, which I can rewrite as m g rho g times r naught cube, which is nothing but W by gamma r naught cube, where W is the weight of the machine plus foundation system and gamma is the unit weight of the soil. So, on further simplification we can write it as W by gamma r naught by pi into pi r naught square. Now, what it can be further reduced to W by A times pi by gamma r naught, because pi r naught square is nothing but the cross sectional area A, that is why we can write W by A. Now, pi goes up, pi by gamma r naught. Okay. Now, what is this W by A? W by A is nothing but, as per Chauvet-Turiaf's expression, this is Q naught. Q naught times pi by gamma r naught, that is equals to this B. Now, let us see what other simplifications we can make from our known expressions. A naught n is expressed as omega n r naught root over rho by g, that we have already used. This omega n we can write as 2 pi f n r naught root over rho by g. Therefore, A naught n square will be 4 pi square f n square r naught square times rho by g. So, if we simplify the expression of B A naught n square, in this case what we will get? 4 pi cube r naught f n square by g g into q naught, by putting the expression of B. Therefore, on further simplification we can write it as 4 pi to the power 2.5 root over A by g g into q naught f n square. So, I have taken out root A, which is nothing but pi to the power 0.5 times r naught. Is it correct? Next, what I can mention in this case, that f n square times q naught is nothing but g g by 4 pi to the power 2.5 root over A times B A naught n square. Just I have taken B A naught n this side and this parameter on the other side. Therefore, the Chauvet-Turiaf's design chart in the x axis, which is f n root over q naught can be written as root of g b a naught n square by 4 pi to the power 2.5 times 1 by 4th root of a. Okay. This can be written from here easily by taking root from both the sides. Now, for vertical mode of vibrations, b a naught n square is can be simplified and written as 4 by 1 minus mu, that we have seen in our problem number 1 also. So, what further simplification we can do for this expression? Let us see. So, f n times root over q naught can be expressed as root g times 4 pi to the power 2.5 into 1 minus mu times 1 by 4th root of a. Okay. Or 1 by 4th root of a is equals to root over pi to the power 2.5 1 minus mu by g into f n r. By taking this term over there, we can write like this. This one is nothing but our tan theta. Therefore, in the plot of this y versus x in Chebotarev's plot, that tan theta is nothing but proportional to this term pi to the power 2.5 times 1 minus mu by g, which is proved. Okay. So, if we look at the slide, what it was asked here, that tan theta is proportional to pi to the power 2.5 into 1 minus mu by g, which we have established through the analytical solution. So, that completes the answer of this question number 3. Now, let us move to the next problem, problem number 4. Question 4 says, compute the factor of safety against liquefaction using the approach proposed by or given in the paper of Yu et al. 2001, which we have discussed in this course while discussing the theory part. At a depth of 10 meter below the ground surface, for earthquake moment magnitude m w equals to 6.5, at a site with following available field data, that is depth of water table below ground surface is 5 meter, soil type loose silty sand with percentage fine is 6%, gamma saturated is 17 kilonewton per meter cube, friction angle of soil phi is 31 degree, relative density dr is 60% with the factor f equals to 0.7, which we need to use for some correction later on. I will describe. The SPT value, standard penetration test value given to us is N60, that is, it is corrected with respect to the energy correction N60 at 10 meter depth below the ground level is given as 14, and earthquake zone 4 as per our Indian seismic code of IS 1893 with A max value given as 0.24 g. Let us see how we can proceed to the solution of this problem. Let us first write down the given parameters for this problem number 4. We are writing N 60 is given as 14, A max is given as 0.24 g. Now, let us assume or consider that gamma saturated equals to 17 kilonewton per meter cube above groundwater table also. That is, when the data is not provided, we can assume reasonable value of gamma. If somebody wants to consider some lower value of gamma above groundwater table, or if the value is provided to us, we can use that exact value. In other words, we can use either gamma of 17 maximum above groundwater table or little lower than that value as per actual if it is given to us. And the depth at which we need to compute this factor of safety against liquefaction is 10 meter. Now, what is the total stress in the soil element at that 10 meter depth? Sigma V is nothing but 17 times 10, which is 170 kilonewton per meter square. And what is the effective stress? Sigma V dash at 10 meter depth, 17 into 5, which is up to the location of groundwater table, because in the question paper it is mentioned groundwater table is at 5 meter depth below the ground surface, plus we need to take the submerged weight 17 minus 10 into 5. You can note here, I have considered unit weight of water as 10 kilonewton per meter cube. If somebody wants to consider as 9.81 kilonewton per meter cube, that is also correct. One can consider that as well, but for the simplicity we can consider 10 also, which computes to be 120 kilonewton per meter square as the effective vertical stress at the depth of 10 meter, which is more than 100 kPa or 100 kilonewton per meter square. This value of 100 is necessary because later on we will see, based on this value we need to decide whether we should go for some particular correction in liquefaction computation or not. So, let us proceed to the calculation of various terms. So, as per the paper of Yude et al. 2001, which we have described in detail and discussed for liquefaction computation, the R d, that parameter R d, due to the flexibility of the soil which needs to be considered, is expressed for 10 meter depth. We can use this expression. So, the value of R d at 10 meter depth will be 0.907. And what is the expression for CSR, cyclic stress ratio, as given in this paper? We know CSR is 0.65 times A max by g, g is acceleration due to gravity, sigma v by sigma v dash times R d. So, all these parameters we know. So, we can calculate CSR very easily. 0.65, it is given to us, A max is 0.24 g this is also G. So, this gets cancelled. Sigma V is 170, sigma V dash is 120 and R D is 0.907 as we have computed here, which gives us the value of CSR comes out to be 0.20045. That is the value of cyclic stress ratio. Now, let us see how we can compute the cyclic resistance ratio, that is CRR, for computation of factor of safety against liquefaction. Before that, the SPT N60 value needs to be corrected further. So, what are the corrections required? The overburden correction Cn is required, because only energy correction is done here. The overburden correction is not carried out. So, Cn, if we take the expression given in the Ude et al. Paper, is this, which is the correction factor for overburden pressure for the SPT N value needs to be carried out, is 0.5, which is 0.913. Now, other correction factors, let us assume or let us consider that CB, CR and CS all are equals to 1, that is no correction is required, because no other information is provided in this question number 4 about the borehole diameter used for this SPT, the rod length and the sampler tube liner material. So, in absence of these data, we can take no correction factor, but if these data are available, suppose a particular borehole diameter is provided, we need to check what should be the borehole correction factor. If a particular rod length for SPT is provided, we need to check what is the CR value, and if the sampler lining condition is given to us, we need to check what is the value of this correction factor. So, we can write down N160, which is corrected SPT value, including energy as well as overburden and all these correction factors, becomes 14 times 0.913, which is 12.8. Now, this is the correction of SPT N value statically. Now, we need to do further correction, which requires the percent fines correction as proposed in the paper by Ude et al. 2001 for clean sand condition, because we need to convert this N value, corrected N value, to equivalent clean sand condition. So, let us see what should be that correction. So, fines content is given to us as 6% in the problem, whereas the correction or corrected value of N160 clean sand is expressed as alpha plus beta times N160. So, in this case, alpha is the parameter which can be calculated using this expression, because we know in this case percent fine is more than 5% and less than 35%. That is the range, as we remember in Ude et al. Paper is given. So, for that range between 5 to 35% of fines, this is the expression of alpha needs to be used, 1.76 minus 190 by f c square. So, 6 square, which gives us 0.0297, and the expression of beta for this range, that is percent fine within 5 to 35% is given by this one. Now, this on calculating these values we get 0047. If I compute these two value and put it here with the known value of N 160 which we have calculated, we will get what is corrected value of N 160 with respect to clean sand condition. So, let us see how much is the value of that N 160 CS. So, N 160 clean sand comes out to be 0.0297 plus 1.0047 times 12.8. This is N 160 we had calculated already, which gives us 12.9. This clean sand value is less than 30. Hence, check against liquefaction hazard needs to be done. That is the conclusion one can made here itself as a design proposal, that any site which is having N 160 clean sand value less than 30 needs to be checked against liquefaction potential. So, now if we use the equation for CRR, that is cyclic resistance ratio at 7.5 moment magnitude of earthquake as given by Yu et al. In the paper, it is given as this N 160 by 135 plus 50 by 10 times N 160 plus 45 whole square minus 1 by 200. That is the expression for CRR. Here we need to use in this N 160 the value of N 160 CS, because that is the clean sand condition value. See, if we put that value of N 160 over here, what we will get? Let us see. So, the CRR 7.5 comes out to be 0.1396. With this value, now if we check other correction factors like Km, Km is magnitude correction factor for this CRR, because in our given problem what was mentioned, we need to compute, if we look at the slide here, we need to compute for earthquake moment magnitude MW of 6.5. So, a magnitude correction factor Km is necessary, because it is for 7.5, we need to find out for 6.5. The expression for Km is 10 to the power 2.24 by MW to the power 2.56. So, that gives us 6.5 to the power 2.56, which is 1.442. That is the correction factor for magnitude. Now, another correction factor we need to find out here, that is K sigma, which is given as sigma V dash by P A to the power f minus 1. This is overburden correction factor to this CRR needs to be applied, as we have discussed in the theory. Sigma V dash, if it is more than 100 kPa, then only we need to incorporate this. In this present case, it is 120 kPa. So, we need to apply that, and F factor is given in our question as 0.7. So, if we compute it, what we will get? The K sigma is 120 by 100 to the power 0.7 minus 1, which gives us the value of 0.9468. Now, considering or assuming K alpha, that is due to the slope, the correction factor is 1, because no information about the sloping ground condition is provided in the problem. In that case, we can take as 1. So, factor of safety against liquefaction is expressed as CRR 7.5 by CSR times this correction factor K m, K sigma and K alpha. So, if we put all our known values, what we will get 0.1396 by 0.20045 times 1.442 times 0.9468 times 1, which gives us the value of 0.95. So, for the given problem at 10 meter depth, if an earthquake of magnitude, moment magnitude of 6.5 is expected at 10 meter depth with the given soil condition, factor of safety against liquefaction will be 0.95, which is less than, of course, 1, also less than 1.3, which we generally use for design of any structure in that particular soil, any foundation, anything we want to construct in a particular soil. The factor of safety against liquefaction must be equal to or above 1.3, which is not the case here. So, what should be our comment? This is the answer of the problem, but if we want to comment on this answer, the comment should be any foundation will not be suitable if we want to put it in the same soil condition at 10 meter depth in terms of liquefaction is concerned with moment magnitude of 6.5 at that site. So, that will be the conclusion. So, with this we have come to the end of the solutions of this quiz, and this quiz of 100 marks can easily be solved. As we have seen in the slide, this problem carries 40 marks. So, it completes or ends the solution of quiz. After completion of all the 7 modules which I have taken for this course on soil dynamics, the technical part of this course on soil dynamics has come to an end, but this course on soil dynamics will really not be ending if I don't acknowledge few people who has helped me in several ways to come out with this soil dynamics course, which I have given the lecture in this video course. So, the acknowledgements which I want to put on record for this soil dynamics course first goes to my teachers, from whom I have learnt during my student days this topic of soil dynamics and machine foundations, namely my teacher Professor A. Sridharan, then my teacher Professor K. S. Subbarao and Professor Jayant Kumar of Indian Institute of Science, Bangalore, India, which is commonly called as IISc Bangalore. They taught me this subject in several ways during my master's and PhD program for the application and the theoretical aspects of the soil dynamics and machine foundation aspects. Also, I would like to put on record the name of Professor Nitin Som and Professor Falguni Bhattacharya of Jadavpur University, Kolkata, India, where I did my bachelor's degree, and during the bachelor's in the 4th year in one of the special course on design of foundations elective course, there was a small portion on machine foundation, from which I got my first step of learning in this problem of soil dynamics. So, first acknowledgement goes to all my teachers whom I have mentioned over here, and the next important acknowledgement, without whom I could not probably had given this video lecture on soil dynamics, are all my students. As we all know, for us, that is we are the teachers, the students is the main backbone for our any activity, whether it is research or teaching. And in IIT, we mostly learn through teaching process as well, not only from research, but also through teaching, by teaching these exceptionally brilliant students of IIT, And for this course also, I must acknowledge the contributions or the suggestions or the questions came out from the student community, which I am teaching in this institute of IIT Bombay from several years, last about 10 years or so. So, I should put in record the name of the students like Kaustav Chatterjee, Ritika Sangroya, V. Dilli Rao, Amay Kadare and Debarghe Chakrabarti. These students had helped me to prepare the slides which I have presented during this video lecture, and also to check the several parts of the video and its output etc. at different point of time. Also, I want to put on record my former students like Dr. Sanjay Nimbalkar, Dr. Syed Muhammad Ahmed, Mr. Shantiram Chatterjee, Ms. Somdatta Basu, Mr. Rajiv Bharti, Mr. Siddharth Chauhan of IIT Bombay, Mumbai, India, who worked with me under various capacities like either as my former PhD student or my former master's student or my former BTech project student, and who came out with subsequent number of or some new input in this world of soil dynamics, which gave another new approach of various analysis which I have discussed throughout this course at some of the portions like design of retaining wall considering mass spring dashpot model, then behavior of railway subgrade soil by considering mass spring dashpot model, also for the slope stability aspect etc. So, I must acknowledge the contributions made by these students during the process of teaching and research on this topic of soil dynamics and machine foundations. My next acknowledgement will go towards my collaborator. You can see here where I have visited as Boyce Cust Fellow at University of California, Berkeley in USA. So, there my research collaborator was Professor Jonathan D. Bray, whose lecture on geotechnical earthquake engineering and soil dynamics also helped me to get the input on this subject, some of which I have tried to provide in this video lecture also. Last but not the least, I want to put on record the help provided by CDEEP of IIT Bombay, NPTEL program of MHRD Government of India, and all my colleagues and friends of my institute, present institute IIT Bombay, and my former institute IIT Kanpur, who had helped me in various capacities while providing this video lecture on soil dynamics through their expert comments or criticism, or how to improve the quality of the presentation and lecture topics etc. etc. So, if any one of you are interested to contact me, here I provide the further contact details. This is my name, Dipankar Chaudhary. I am a professor in the Department of Civil Engineering, IIT Bombay, Powai, Mumbai, 400076, India. This is my postal address. My telephone number is +9122 2576 7335. This is my office number, and +9122 2576 8335 is my residence number. You can also reach me via email. My email IDs are dc@civil.iitb.ac.in or dchaudhary@iitb.ac.in. Also, you can reach to my website, which is available at this URL, where you will get the details about my teaching, research and various other administrative, academic and professional activities in this field of soil dynamics and machine foundations. So, with this we have come to the complete end of this course, video course of soil dynamics for NPTEL. Thank you.